Welcome. I am Riganko Devnath and today we will discuss Windows 11 through the lens of operating system design principles. We will explore its architecture, resource management and security and how it balances performance with a seamless user experience. Let's dive in. Coming to OS structure and kernel design, Windows 11 adopts a hybrid kernel merging the efficiency of monolithic design with modularity. Unlike pure microkernels, it keeps critical services like the hardware abstraction layer in kernel mode for speed, while isolating drivers in user mode for stability. This structure supports system calls to the Windows 32 API and Windows Driver framework, enabling apps to interact with security and hardware. For instance, the virtualization-based security uses hypervisor-assisted isolation to protect kernel memory from exploits, a direct application of protection mechanisms. Notice how critical processes like system and registry run in kernel mode while third-party apps run in user mode. This separation minimizes crashes and aligns with protection and security principles. Coming to process scheduling and CPU management, Windows 11 uses a preemptive priority-based scheduler. It dynamically adjusts the thread priorities using the Windows Thread Simulator, favoring foreground apps like Teams or Edge for smoother user interaction. For hybrid CPUs like Intel's P-Core and E-cores, the dynamic load balancer assigns the compute heavy tasks to performance cores, while background services like updates use efficient cores. This reduces power consumption by up to 30% for laptops. Unlike static round robin, Windows 11 Scheduler adapts to workload changes, preventing deadlocks through smart resource allocation, which is more core concept in deadlock avoidance. Coming to memory management and virtualization, Windows 11's memory management uses a demand paging and compression tool to reduce page faults. When RAM is full, it compresses idle pages instead of writing to the page file, cutting latency by 50%. The segment heap allocator optimizes memory for modern applications. For example, tabs run as isolated processes in Edge browser, each with dedicated heap, preventing one tab crash from affecting the others. Virtualization is central in Windows 11. The Windows subsystem for Linux leverages Hyper-V to run Linux kernel in lightweight VMs. Unlike other VMs, WSL2 uses dynamic memory allocator, freeing resources when not in use. A perfect example of container virtualization. Coming to file systems, Windows 11 uses NTFS and REFS. NTFS uses journaling to log changes before committing them, ensuring data integrity during crashes. REFS uses enterprise storage, adds checksum to detect corruption automatically. The direct storage API bypasses CPU bottleneck by letting GPUs access directly to NVMe SSDs. Games like Forza Horizon 5 load 40% faster due to disk scheduling algorithms, minimizing seek time and rotational latency. Concurrency and synchronization. Windows 11 handles inter-process communications via named pipes and Windows sockets. For synchronization, it uses spin locks for short waits and mutexes for longer takes. Bakery algorithm inspired its fairness into thread scheduling, ensuring no process stops. For example, Windows Audio Driver Graph uses priority-based semaphores to manage real-time audio streams without glitches. Windows Runtime APIs implement monitors to solve classic synchronization issues like the dining philosopher problems, ensuring thread-safe resource sharing. Coming to security and modern threats, security in Windows 11 is multi-layered. Windows Hello uses facial recognition using infrared 3D mapping for authentication, while BitLocker encrypts disks using AES-256 and TPM 2.0 chips. Core isolation uses hardware virtualization to create a secure sandbox for critical processes, blocking zero-day exploits. The smarter control blocks untrusted scripts, enforcing the access mutex model from our knowledge. Contemporary trends and future directions. Windows 11 embraces contemporary threads. The Windows subsystem for Android runs Android apps in containers while Snap layouts optimize screen space using adaptive process prioritization. With ARM support, Windows 11 scales efficiently on low-power devices using machine learning to predict resource allocation like preloading frequently used apps into memory. From its hybrid kernel to AI-driven resource management, Windows 11 exemplifies modern OS design principles. It's not just an OS, it's a bridge between user needs and hardware innovation and robust security. Thank you.